All right. Let me give you a very simple example. So I'm going to go in 2 phases. I'm going to first talk about estimation of orientation, and then I will talk about estimation of orientation plus translation. So turns out orientation based on current technology is easier than translation in terms of estimation. It's a bit surprising perhaps, but that's the way it works. So estimating and let's jump down to a very simple case, the 2D case, which in terms of space of orientation is just one dimensional. So imagine I just have a spinning wheel and maybe I have some kind of marker on this wheel that's pointing in some location, and I will say that that's at initial orientation theta 0, and over time this wheel starts rotating and it ends up being at some angle theta. Maybe I can make it look like it's time parameterized by putting theta of t. So this wheel is spinning and maybe its rate's changing as it goes. So I say time t equals 0, theta equals theta 0, and at t greater than 0 it has a rotation rate let's just say it's constant to start. So rotation rate is omega radians per second. So omega using calculus is just d theta dt. So just the angular velocity. So if that's the case, then theta of t, if I write theta as a function of time, is just whatever my initial theta is plus omega t, right? So that's all. So how long has it been going for? Multiply that by the rotation rate, and that will give me the total amount of rotation in terms of radians. So let's see here. All right. Now what if omega varies over time? Then theta of t is just theta 0 plus the integral from 0 to time t omega of, I don't want to put a t inside of here because it's an integral, so give some other parameter s ds, right. So we just now write omega as a function of time and we just integrate that, right. So that's all simple calculus, and I haven't really computed anything here. So it's just, you know how it is in calculus, it's so much easier to write things down than to actually do anything with it, right. As soon as you have to actually do integrals, you're in a lot of trouble, right. They only show you the ones that work, right. So all right. So of course what we do in actual computation is we make a discrete time approximation and if that's the case, then we end up with something like the following. We may say that theta is approximately equal to theta 0 plus a sum. I goes from 1 to, let's say, k, some step delta theta sub I, which I will just use some change in notation, say that's equal to, again starting at theta 0, I goes from 1 to k of omega I times delta t, and I expect delta t to be some fixed sampling rate, so maybe delta t is equal to 1 millisecond. This is a common sampling rate for accelerometers and gyroscopes that are used in these kinds of tracking systems. So that's a very practical and common number. And then my omega sub I is just some sampling then. Let's say that's my omega function that I drew here when I was trying to do calculus at some particular time index, maybe I minus 1 times delta t, whatever. So just some particular time stamp that this omega I corresponds to. So that's how I estimate my theta of t. Let me put theta of t over here, theta of t, right? And this k goes, this is the highest k I can get to before advancing beyond time t. Now, so that's the scenario I have. So I must lose something by doing a discretization here, right? So this is going to be a simple Euler integration discrete time approximation to this integral. So that's one place where I've lost some information. Another thing that's going to happen is I'm going to assume that I cannot actually accurately measure the angular velocity, but I get a sensor that tells me the value. The sensor is going to have limited precision. It's going to have noise issues, calibration issues. So I get some sloppy numbers, and I'm going to do this kind of numerical integration by just trying to estimate the change in theta. How much did theta change in each millisecond? And I just want to add that up. Is that pretty easy? Sound reasonable? Right, so that means that what I'm really trying to do is construct some theta hat at some given time. I might even start to get confused about what time it is, in fact, but I don't want to get too crazy here. And so that will be theta 0 plus sum I equals 1 to k omega I hat. I'll put a hat on it to indicate that it's an estimate. So measured by a sensor, measured by some kind of filter, probably not correct, but it's the best guess I have. That's what hat is going to mean. Delta t, where this is the sensor reading from a one-dimensional gyroscope. Right, so a gyroscope that's just going to report a scalar quantity that is the yaw in radians per second. Right, questions about that? So this should make sense, right? So imagine this wheel is turning here like a turntable or a merry-go-round. So it's turning around, its rate's varying. We hook up some kind of one-dimensional gyroscope. We put it on top of this disk and it starts spinning, and it takes measurements for us. Does it matter where we put it on the disk? Should still report orientation changes the same way, I believe. Maybe its accuracy might be affected by where it's at, something to think about, but depends on how the device is engineered. If we place it there, we get these measurements out, and then we're just accumulating, numerically integrating in the simplest way possible. I'm not using trapezoid rule and Simpson's rule and other kinds of fourth order Runge-Kutta and other things like that to try to approximate it better. I'm just doing simple adding up of the measurements. Keep it simple here. All right, does that seem fine? Now, I'd like to do the 3D version of this, and I'd like to not get lost in an enormous mess of 3D rotations. I'd like to not be dragged through a bunch of trig functions and yaw, pitch, roll, and singularities. I've seen a lot of mess out there on the internet, in fact, when I search for different methods for integrating gyro readings. It turns out it's very, very simple if you've already committed to using Quaternions, and it's kind of a mess if you haven't. So let me just show you a very, very simple way to do things. If you have a Quaternion library ready to go, it ends up doing the exact same thing here, but just with like a couple of lines of code. Just like this would be a couple of lines of code or software, the 3D case ends up being simple like that as well, if you understand the principles we've covered already on 3D rotations. Okay, so now look at 3D. 3D orientation case. Remember Euler's rotation theorem, which is every 3D rotation can be represented as a rotation about some axis through the origin and some angle about that axis. And there's, of course, two different ways it could be done depending on which way the axis is oriented. That's okay. We could reverse the axis. So some axis through the origin and some amount about that axis. So I'm trying to estimate the orientation of the head if I want to make a perfectly portable VR system. A lot of VR systems right now work with smartphones that are just dropped into a case, right? Google Cardboard, Samsung Gear VR like that. Many others are out there. There's a lot of open source ones that are out there. So, so basically if you just use these gyroscope sensors, and additionally you can use accelerometer, magnetometer, which we'll get to, but if you just use these portable sensors on the phone that are based on MEMS technology, then we're just tracking orientation. That's about all we can reasonably get from this. So if we look at the gyroscope measurements, we get draw here to the side. We have what's called a 3-axis gyroscope. So we have 3-axis gyroscope measurements or readings. I said readings there. Let me do readings. So we get some vector omega. I wrote omega as a scalar here. I'm going to write it as a vector here. So we get these readings. I guess I'm not going to write it with a hat yet. I'm just going to talk about 3D angular velocity for a bit here. So before I actually get to the readings, I just want to say that if we look at angular velocity in 3 dimensions, there's omega x, omega y, and omega z. And I'll draw out my coordinate axes here. Remember that this was the x-axis going to the right, y is up, and z is coming out at us to keep it right-handed. And so what's interesting about angular velocity is that this is the instantaneous rate of rotation about these 3 canonical axes. So if I write, let me just write it out here and describe it a bit. So if I write out omega x as a rotation about the x-axis, in fact rotation rate about the x-axis, omega y is rotation rate about the y-axis, omega z is rotation rate about the z-axis. What I mean is that imagine the 3D body. It's tumbling along, right? It's rotating around, and then at a given time I just take a snapshot of it, and now I project into the various axes. So if I see this object rotating and I take a snapshot of it as projected into the xz plane looking down the x-axis, it will look just like 2D rotation, and when I do that projection it's rotating at some rate, and that rate is exactly what my gyro is going to be measuring. Isn't that nice? Same thing is going to be true for the y part. It'll be if I look straight down on it, what will it look like in the xz plane? How fast is it rotating? Radians per second, single scalar number. It will give me that one. When I look at it in the xy plane looking down the z-axis, it'll again give me a rate of rotation. What is that? That's going to be the omega z component. So it's giving me these 3 instantaneous rates of rotation. It feels a lot like yaw, pitch, and roll rates. However, because it's instantaneous, we don't have to worry about the weird problems of non-commutativity of 3D rotations. This is just an instantaneous measurement of the rates. So they're all happening at the same time. There's no ordering problems or kinematic singularities. We're not putting them all together as part of a sequence of matrices to perform the operation. It's just an observation about these rates. So at that instant, I want to know what is the rate of rotation, so that if I put these all together, I should be able to extract a single axis, 3-dimensional axis, and a rate of rotation about that axis. And that, if I can get that, that'd be beautiful. That'd be just like what I had in the 2D case. The axis of rotation in the 2D case is always the z-axis, right? Because it's the third axis. It stays the same. Here, remember, this axis should be changing over time, and I'm looking at these rates in a single snapshot. So here's what happens. It's really quite beautiful. Shows up in textbooks. Mathematicians know this. Doesn't show up enough on the internet, sadly, in terms of answers to people's questions on forums. Just the following. So so let's just assume for a bit that omega is constant over delta t. I don't want to allow omega to vary during 1 millisecond. So let's just assume that it's constant. And so if, of course this is an approximation, but if omega is constant, delta t, then how much rotation has occurred? Then the rotation is by some amount delta theta. So I'm going to tell you how much rotation there was. Delta theta is going to be this kind of theta. It's axis angle representation. It's going to be some amount of rotation. The amount is going to be exactly the length of this omega vector times delta t. All right, so in other words, it's just square root of omega x squared plus omega y squared plus omega z squared times delta t, which is 1 millisecond, 0.001 in the case of most MEMS gyros that people are experimenting with right now. So that's very interesting. So that suggests that if I just take the length of this vector, that's going to give me the overall rate of rotation. This makes good sense because each one of these is in radians per second, and if I take the overall length of this, that's the total amount of radians per second. If this object stops rotating, all three of these components become 0, which makes good sense, right? There's no rotation at all. If it's rotating only in the xy plane, then the omega z component will have all of the rotation. When I take the length, I just get exactly that part. So this is giving me the overall amount of rotation in radians per second, and this will be the amount of rotation that occurred in time delta t. The instantaneous amount, the instantaneous rate as a scalar is just this magnitude here. But the question is, what's the axis? And what's very interesting about this is that the axis say v is just taking this vector and normalizing it. So the direction of this vector is already the instantaneous axis of rotation. So it's crazy. There's like no work to do. It's already being given. I'm not deriving the mathematics of this. I'm just giving you the result with some intuitions along with it. So if I just renormalize this vector here, so because I said I wanted the axis to be a unit vector at some point earlier when I was covering these things. So if you don't like to normalize it, you don't have to, as long as you know. So you just divide by the magnitude. Be careful of dividing by 0. If all three components of omega happen to be 0, then there is no instantaneous rotation happening, which you just handle it as a special case. Even in the software, you handle it as a special case. So this ends up being the axis of rotation during this interval, corresponding to this interval delta t. So I said omega is constant. If it were not constant, then the v would be changing, and this whole approximation would fall apart a bit, right, if it changes too significantly. So I'm assuming that delta t is so small that the amount of change in omega is insignificant, and all I'm going to do ultimately is get measurements of omega from my 3-axis gyroscope, 3D gyroscope. So I can now say let delta qi be the Quaternion representation of this axis, let's say at step I, and this delta theta at step I. Is that all right? So in the 2D case, I was just happy talking about delta theta sub I. Now I have to talk about some axis v sub I in addition to delta theta. Does that make sense? Because in 3D, it's the axis that we have to recover in addition to just the amount of rotation, right? So the amount of rotation radians per second, we're trying to estimate that, but we also have to keep track of this axis. Luckily, this 3-dimensional gyroscope, if it provided a perfect reading, it would be giving me the 3 components that I use to directly construct the axis. So if I just take, for example, in software, I may have a Quaternion library that I just pass delta theta and v to, and it'll immediately return back the Quaternion that corresponds to. That Quaternion, in most cases, will be fairly close to the identity. Why is that? Because this is a tiny rotation, right? How far is it going to rotate in 1 millisecond? So just like if your intuition in the 2D case, it's only rotating at some reasonable rate, let's say. You know, how fast is your head turning? So in 1 millisecond, it's not going to get very far. So this is going to be a quaternion where delta theta is small and the axis of rotation. In fact, most of us, if we're doing this most of the time, then it's going to have the largest component corresponding to yaw, right? But if you do some of this, then fine, you get a pitch component and so forth. But so now what we want to do is integrate these readings. Let me write back the 2D case, and then I want to show you how simple the 3D case is once you've been tortured by quaternions, right? Which is, I don't think it's torture, but some people sometimes react that way. All right. So integrating sensor readings to estimate orientation. So I gave you the 2D case, so recall the 2D case, which in terms of orientations was really a 1D case. I said that our estimate of theta at some particular time t, which I guess I've not been too explicit about how that's related to k, but theta 0, although I did say that it's the, we'll consider k all the way up to the current time and not beyond it. So we have I goes from 1 to k. I wrote this before, and it will be the delta theta hat sub I. And you may recall that I said that that is equal to omega I hat delta t, correct? And now for 3D, here's what's going to happen. So 3D case, we have, let's say, q hat at some particular time t is equal to, we already have one problem. I promised you it wouldn't get too complicated, but there's one small complication. 3D rotations are not commutative, and if you remember, things that come later we have to write on the left side, right? So we go from right to left. So that means that if I write a sum, if I were to write this sum out here in the usual way up here for the 2D case, I would go theta 0 plus delta theta 1 hat plus dot 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 dot. I can't write it like that. I have to write it in the other direction, so to make it match up. So I guess I could write this one out like this. I could write delta theta k hat plus delta theta k minus 1 hat plus dot 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 all the way down to let's see, delta theta 2 hat plus delta theta 1 hat plus theta 0. So I'm going to write this one in the other direction because up here I do have commutativity. So I might as well just write it in the other order so that my pictures match up in a pretty way. So that's what I want to do. So if I do that, I'll get down here. This will be equal to delta qk hat. I'm putting hats on it because it's coming from sensor readings. Quaternion product delta q k minus 1. Quaternion product dot 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 quaternion product delta q2 hat quaternion product delta q1 hat quaternion product q0. So how's that? That's how it looks. And now my delta q, I've given you delta qi is the quaternion representation of this v sub I and theta sub I. So each one of these, I guess I didn't even write it out with i's here. I only wrote it out with k. That's fine. I'll just say this is equal to k. I guess I put an arrow and a hat on that because it's an estimate coming in. And delta theta hat k. So that's what each one of these is. this quaternion that I've constructed in each step. So that's all I have to do is just keep multiplying my quaternions, or if you want you could have converted them into matrices and just multiply all the matrices together if you like as well. As I said, there's a lot of advantages to staying completely inside of quaternion land with the algebra, so we can just do it all with quaternion multiplications and keep propagating this forward. There's another nice way to look at it, because when we're writing code, each time we get a new measurement from the sensor, all we need to do is update our previous estimate incrementally. So if we think of it in that way, we can write it like a nice recursion. So recursively, in 2D, we might say our current estimate, I'll just write word subscripts here, our current estimate is equal to the change that's occurred in the last millisecond in terms of our estimates plus whatever our previous estimate was. Correct? So that's just one very simple way to look at it in the 2D case. I just get the current change and just add it to the previous estimate. That gives my new one. So I have a very small piece of software that just takes how far I think I've rotated in 1 millisecond and adds that on. That's all we do each step. So this is just looking at it in recursive or incrementally if you like. Doesn't look like a recursion too much because I haven't used the proper kinds of subscripts. In the 3D case, Q current is just equal to the change quaternion producted with my previous estimate. Right, so there's our nice sort of result for the day. You just estimate what the tiny change was in 1 millisecond in terms of axis and angle, which you can directly read from the gyro. You just take the magnitude of the 3D gyro reading in radians per second. That tells you how far you've rotated, and then you look at the direction of that 3D vector, and that tells you the axis of rotation. You form a simple quaternion, just multiply it on, and you just do these simple updates. When you do that, you're integrating the gyro readings. Questions about that? So what happens if I keep doing this for I don't know, say 10 seconds or an hour? Errors tend to accumulate, right? It may be the case that my gyro has a little bit of a bias to it based on the temperature or based on the packaging stress. There could be all kinds of reasons for that. So if there's some kind of bias, it'll start to accumulate. Maybe it's just a bunch of noise that accumulates over time, so that we start to get what are called drift errors. So the problem that occurs is drift errors. A lot of people may know this as dead reckoning errors. This is a term used in robotics and other fields. For example, it's been around in navigation for many, many years. Dead reckoning error. Reckoning. So drift error, dead reckoning error, same thing essentially. So these are equivalent concepts. So how do we correct for something like that? Well, if you have no other sensors at your disposal, you're not going to be able to correct for it. Right? So we need to get more sensors from somewhere, and I'm going to talk about that in the next lecture. So I'll open up with going into drift correction techniques, which will help compensate for these drift errors. So if we have another signal coming in that can tell us errors, gives us some kind of estimate of the errors that are accumulating, we need to figure out how to apply some kind of correction. If you're not careful, you could accidentally apply the corrections in a way that nauseates people. So imagine you have errors accumulating and now the world's becoming tilted. You decide to quickly apply some tilt correction, and that causes an optical flow that makes people feel like they're on the ocean on a boat. Right? So that could be very bad. So there's a kind of delicate balance between applying drift corrections and making sure that it's perceptually comfortable. So we'll have to get into that for next time. Thanks.